Hi everyone, and welcome to the learning curve. In this lesson I will be doing an illustration of how to solve a quadratic equation by expressing it in vertex form and then using that information to sketch the graph of the quadratic equation. This question is drawn from the Caribbean Examination Council CXC CSEC past papers. And these are very common mathematics questions that appear on these papers. So here we are given the quadratic equation, which is in standard form, x squared minus 6x plus 7. And we're firstly asked to express it in vertex form, a into x minus h all squared plus k. So let's go ahead and write the quadratic equation that we're given here, which is x squared minus 6x plus 7. And what we will be required to do here, in order to express it in the form a into x minus h all squared plus k, is to apply the technique of completing the square. So completing the square is required to express this quadratic equation in the vertex form a into x minus h all squared plus k. I have done previous lessons on completing the square and will do future lessons on the topic as well. But this will also help us to concretize our understanding of completing the square, because it's required to express this quadratic equation in the vertex form a into x minus h all squared plus k. So to do this, we're going to complete the square. So we're going to identify the value of b in this quadratic equation. And the value of b in this quadratic equation is the coefficient of x here in the middle, the term that is multiplied by x, in other words. And that value is negative 6. So that is the value of b. And the next thing we're going to do is that I'm going to take b divided by 2. So this is necessary. Once you've identified b, then divide the value of b by 2. This is negative 6 divided by 2. Yes, negative 6 divided by 2 here, which is going to give us negative 3, which is a very important number, as you will see shortly. So again, the first thing you want to do when you're given a quadratic equation and you're asked to express it in the vertex form is that you want to apply the technique of completing the square. To do so, you first identify the coefficient of x in the middle of the quadratic expression, and that is b equals negative 6 in this case, and then you divide that value of b by 2. So we take b divided by 2, which is negative 6 divided by 2, which is 3. And another thing we want to do is to square this result. To square the result of dividing b over b by 2. So the result of dividing b by 2, which is negative 3, we want to square that value as well, which is 9. Because negative 3 all squared means negative 3 multiplied by itself, which gives us 9. So these are the first 3 things you want to do when you are applying the technique of completing the square to a quadratic equation. Write down the value of b, which is the coefficient of x, divide b by 2, and then square that value. And we're going to use these 2 values now as we proceed to complete the square. So the next step in completing the square is to rewrite the quadratic equation x squared minus 6x. Now I'm going to do a separation of variables here. So x squared minus 6x, I'm going to separate those variables from the constant. So x squared minus 6x, I'm going to add 9. That is, add the 9, which is the square of b over 2 here. We add that 9 to the variables in the quadratic equation. And the variables are the terms which are paired with x. And in this case, that's x squared minus 6x, which I have bracketed here. So add the result of squaring b over 2, which in this case is 9, to the variables. Then we'll have plus the constant, so let's keep that in parentheses. Then it will plus the constant of 7. And then in order to keep the equation balanced, I will have to subtract 9. Because we added 9 to the variables x squared minus 6x, because we added the 9, we have to keep the equation balanced. And in order to keep the equation balanced, we will have to subtract the 9 from the constant that was isolated here, which is the 7. And that now provides us with a balanced equation. The next thing we want to do here is that we want to identify the factors of x squared minus 6x plus 9. And the factors of x squared minus 6x plus 9 here, which is the modified quadratic that we have derived, x squared minus 6x plus 9, we want to simply write down the factors for this quadratic. And this is simply done by identifying the value of b over 2. And the value of b over 2 here was negative 3. So in order to write the factors of this quadratic, we're going to identify the value of b over 2, which is negative 3. And so therefore, the factors of this quadratic, which will be in the form of a perfect square, would be x, always x, then plus b or minus b, depending on whatever the result for b is. In this case, b is negative, so it's going to be b over 2 rather is negative. So we'll have x minus 3 all squared. And those are the factors of this quadratic, x squared minus 6x plus 9. Again, how we derive this x minus 3 all squared is that we look for the result that we got from dividing b upon 2, which is negative 3. And then we just basically take that value, 3 from x, all squared. If this result was a positive 3, then I would have x plus 3 all squared here. But since it's a negative 3, I have x minus 3, and it's all squared. Because the factors, the whole idea of applying the principle of completing the square is to allow us to be able to get a perfect square. And the perfect square will always be found by as x plus or minus whatever you get for b over 2. In this case, we got a minus 3 for b over 2. So that is why the factors that constitute the perfect square would be x minus 3. That's how we got that x minus 3 here. And because a quadratic equation will have two factors, it will be x minus 3 all squared, which means x minus 3 multiplied by x minus 3. So that is the logic behind the derivation of the x minus 3 all squared. So what we'll have here is x minus 3 all squared, which represents the factors of this quadratic, x squared minus 6x plus 9. Then we're going to simplify the constant portion here, which is 7 minus 9. And 7 minus 9 there is going to give us negative 2. And we're going to set this result equal to 0. So what we have now derived here is the quadratic equation in standard form. In vertex form, rather. The quadratic equation in vertex form has now been derived. So we can write down the values here. The quadratic equation in vertex form, remember vertex form is a into x minus h all squared plus k. That is vertex form. So all we're going to do now is that we're going to write down the parameters. There's an invisible coefficient of 1 in front of this bracket. Always when you see a bracketed term without a visible coefficient, it means that there is an invisible coefficient or an invisible term being multiplied by that bracket, which is 1. So then there's an invisible 1 here in front of this bracketed expression. So what we'll therefore do is that we're going to write down the parameters here. We know that a is equal to 1. That is the coefficient of the parentheses here. We also know that h is going to be equal to 3 because 3 is subtracted from x. And we know that k, which is the constant here, k is negative 2. So this is the result of writing the quadratic equation that we are given in vertex form. A into x minus h all squared plus k. So that completes part 1 of the question. In part 2, we're asked to state the minimum value of the function. The minimum value of a quadratic, which is written in vertex form, can always be stated as the coordinate hk. So the coordinate hk here is going to give us the minimum value. Or if it's a maximum value, then we would still use hk. hk basically represents the vertex. So this is the vertex of the quadratic. The vertex is basically where the quadratic graph turns. So if the graph looks like this, the vertex will be right here. If the graph looks like this, the vertex will be right here. What dictates whether the graph opens up like this or turns down like this is the value of a. If a is positive, then it will turn up like this and therefore have a minimum point. And if a is negative, it will turn down like this and therefore have a maximum point. The graph of a quadratic always takes the shape of a U, a smooth U. In this case, we realize that a is equal to positive 1, which means that the quadratic equation will turn upwards like this and therefore have a minimum. So that's the logic behind there being a minimum in this case. And the vertex of that, vertex being the center point right here, coordinate of the center point, hk, right, hk, and so it means that the vertex here would simply be 3, which is the value of h, and k, which is negative 2. That's how that is done. Right? So that's 3, comma, negative 2. So this is the vertex of this quadratic equation. Next, we're going to derive or determine the equation of the axis of symmetry. Again, I'm going to just do a sketch of a quadratic graph here. The axis of symmetry will be a dashed line passing through the midpoint right here. It's a dashed line, straight line passing through the midpoint that divides the quadratic into 2 equal halves, which are symmetric to each other. Right, so there's equal area on this side and equal area on this side. The area on both sides of the mirror line or axis of symmetry is the same. So this is what the axis of symmetry looks like right there. And we'll be drawing this graph a little later in our computation of this problem. So we have determined the minimum value, and now we're asked to write the equation of the line of symmetry. The equation of the line or axis of symmetry is always simply whatever h is equal to. And h is equal to 3 in this case, yes? So whatever h is always represents the axis of symmetry. So remember, the coordinates of the minimum point is hk, which is 3, negative 2. So it means that the equation for the axis of symmetry, yes, the equation for the axis of symmetry will be x equals 3. X equals 3. Because the coordinate of h, the value of h, which is 3, is always the axis of symmetry. And because the axis of symmetry is a vertical line, then its equation has to be expressed in terms of x. If it was a horizontal line, then it would have been expressed in terms of y. But because it is going to be a vertical line that passes through the vertex of the quadratic, then it's going of the parabola, which is the graph of the quadratic, then it's going to be an equation expressed in terms of x. Vertical lines have equations expressed in terms of x, and the axis of symmetry will occur at the coordinate h, the x coordinate h. So therefore the equation of the axis of symmetry is going to be x equals h. So we can generalize it here. It's always x equal h that will be the equation of the axis of symmetry, which is simply x equals 3 to be more specific. So we've taken care of expressing the quadratic equation in vertex form. We've also taken care of deriving the minimum value of the function, which is the vertex, which will always take the form h comma k, which is a coordinate, h being akin to the x value and k being akin to a y value. So we get 3, -2. And then we determine the equation of the axis of symmetry, which is always going to be x equals h, and specifically in this case x equals 3. And the next thing we're asked to do is to sketch the graph of the function for the domain -1 less than or equal to x, which is less than or equal to 7, or we could say x greater than or equal to -1 but less than 7. So we're going to use up all the space that we have here. So I'm going to divide this section into 2 halves in order to come up with this result effectively. So I'm going to place my graph over this side, and I'm going to do some workings on this side. Alright, so this is a sketch. I'm going to sketch our graph right here on this side. And let's show you how this looks. And we're going to do some calculations on this side so you understand completely what's happening. Let me just redraw this a little bit. There we go. Okay. There. This is our x-axis, and this is of course our y-axis. So to sketch the equation of this graph, and it says we should sketch the equation, we should sketch the graph of this function. Sketch the graph of this function using the domain. The domain is the set of x values over which the graph will span. So already we can go ahead and insert the x values in this graph. So the domain 1, 2, 3, 4, I'm going to go up to 7 because the domain goes up to 7, 5, 6, and 7. Because again, the domain of the graph speaks to the span of x values that the graph will cover. So here we go up to 7. And the x value on this side is -1. So -1 to -7 is the domain of the graph. So this means that the range of, or the band of x values over which we will draw this graph is between -1 and 7. But we do need some other bits of information to be inputted on this graph as well. We need to plot the coordinate of the minimum point as required. We need to also represent the axis of symmetry, and we need to represent the y-intercept. Let's start with the y-intercept. The y-intercept here is going to be 7. The y-intercept is going to be the constant in the original quadratic function that we are given. Right? The constant, that is the value of c. Because remember that a quadratic equation takes the general form, or the standard form, ax squared plus bx plus c. And this is a quadratic equation, c or k, either is fine. So x squared plus bx plus c or k, k representing the constant. And we realize that in this case, the constant c is indeed 7. Linking this quadratic equation to this general form, we realize that the constant term is 7. Said another way, we could say that the y-intercept always occurs wherever the values of x are equal to 0. So if I were to have substituted 0 here for x squared and 0 here for x, then I would just get 0 squared minus 6 multiplied by 0. So I get 0 for both of these, and I'd just be left with 7. So the coordinate of the y-intercept is 0, 7, because 7 is where the graph will cross the y-axis. So the y-intercept is 7. That is the constant term, the number that stands alone, that is not paired with any x, the constant term in the quadratic function. Right? So we have identified that the y-intercept, so let's write it here. The y-intercept, the coordinates of the y-intercept is going to be 0, 7. We'll put them on the graph shortly. Right, so the y-intercept is 0 to 7, 0, 7. Because the coordinate of any point on the y-axis is always an x value of 0 to that value. So in this case, we have identified that because the constant term in the quadratic equation is 7, original quadratic equation that we're given is 7, then it means that the graph will cross the y-axis at 7, or intercept the y-axis at 7. So therefore, the y-intercept is 0, 7. That's our y-intercept, 0, 7. So we have our y-intercept stated, and we will plot it on the graph shortly. And we know the equation of our axis of symmetry is x equals 3, which we'll also plot on the graph. X equals 3 is our axis of symmetry, right? So that's our axis of symmetry. But there's another very important determination that we need to make, apart from the information that we already know. This is our axis of symmetry. And we also know that the coordinates of the minimum point, HK, is our minimum point, which is equal to 3, negative 2, as we found earlier. So 3, negative 2, this is our minimum point. Again, we know that the graph is going to open up because the value of A is positive. If the value of A was negative, it would open downwards. Right, so this is our minimum point, so we can go right ahead and actually plot our minimum point, which is 3, negative 2. So I'm going to go on here and I'm going to put on negative 1, negative 2. So already we know that 3, negative 2 is going to be my coordinate right here. So the graph is going to turn right here at 3, negative 2. So that is what we call the vertex. The vertex is where the graph will turn. So we know the graph is going to turn. So I can just put a little turning symbol through it. It's going to turn and it's going to look something like this. It's going to take a U shape like this. Okay? So you'll see how that works out in a few minutes. We also know that the axis of symmetry, which divides the parabola, which is what the name we give to the graph of a quadratic function, the axis of symmetry which divides the quadratic graph, that is the parabola, into 2 equal halves is going to be at x equals 3. So I can go ahead and draw dotted lines passing through 3 from the minimum point. Passing through 3, I can go ahead and draw my dotted lines. And this is the axis of symmetry, and I'm going to label the equation for the axis of symmetry as x equal 3. That's the equation for the axis of symmetry. But this is our minimum point here, and the coordinates of our minimum point, as we said earlier, is 3, negative 2. So we're labeling all of these to make our graph as self-explanatory as possible to the examiner. The examiner is impressed by detail in your delivery of your answers. So we're going to draw our graph shortly. We know what the y-intercept is, but we have to also make some other important determinations. And the chief determination that we have to make is that we want to know the end points of the graph. The end points. And to find the end points of the graph, which is the parabola, again, the parabola is the name for the graph of a quadratic equation. To find the endpoints, what we're going to do to find the endpoints is that we're going to look at the outer limits of the domain. The outer limits of the domain are -1 and 7. So therefore, to find the endpoints, what we're going to do is that we're going to say when x is equal to -1, what is y? And when x is equal to 7, what is y? Okay, so to find the first endpoint, I'm going to say when x is equal to -1, let's start with the lower limit. When x is equal to -1, y is going to be equal to, and we're going to just use the quadratic equation in vertex form here, x minus 3 all squared minus 2. Say y would be equal to x minus 3. So y is equal to x minus 3 all squared minus 2, which is the quadratic equation in vertex form. So here, x minus 3 all squared minus 2. And we're going to substitute the value of x, which is -1, which is the lower limit in the domain. We're going to substitute it into this function to find the corresponding y value when x is equal to -1. Note that we could have substituted x equals -1 or the outer limits of the domain into the original quadratic equation as well. Keep in mind that this is still y. This quadratic equation in vertex form is still in terms of y, because it is just a re-expression of the original quadratic equation. But we use it to compute the values of y at the outer limits, the values for the outer limits of x, on the basis that it is simpler to do so using the quadratic equation in vertex form. So now what I'm going to do is that I'm going to substitute the value of x here, and when I substitute the value of x, I'm going to get here -1, this is -1 right here, minus 3 all squared, take away 2. Take away 2. Yes. And this is going to give us, so we're going to say now -1 minus 3 is going to be -4. When we square -4, we're going to get 16, and 16 minus 2 is going to be 14. So this all works out to be 14. Again, -1 minus 3 is -4. -4 all squared will give us positive 16, because when we square a negative number, we get a positive number. So this is going to be 16 take away this 2, which is 14. So it therefore means that the coordinate of the endpoint here, the coordinate of the endpoint that is associated with the lower limit of the domain, which is -1, would be -1 being the lower limit of the domain, matching to a corresponding y value of 14. So we can go ahead and plot that shortly. But the second endpoint that we need to locate now, the second endpoint to bring this to a closure, the second endpoint in the domain that we're given, remember that the domain is just the band of x values that the graph will cover. And so the second x value that we're given, which is the upper limit of the domain, x equals 7. So when x is equal to 7, we're going to find the corresponding value for y. So when x is equal to 7, y is going to be equal to, again using this quadratic equation in its vertex form, x minus 3 all squared minus 2, which we derived earlier here. Using that, we will substitute x equals 7. When we substitute x equals 7 here into the quadratic equation in vertex form, we get 7 take away 3. Yes, so that's 7 take away 3 all squared. When we take 7 minus 3, we get 4. Alright, let's not forget the minus 2 here. That is the value of k. So 7 minus 3 is 4. 4 squared will give us 16. Positive 4 squared is going to give us 16. Yeah, so when we subtract 3 from 7, here we get 4. Then 4 raised to the power of 2, which is 4 squared, will give us 4 multiplied by 4, which is 16. And 16 minus 2 is going to give us 14. So we have the other coordinate for the endpoints which is 7, x value of 7 here, and the corresponding y value of 14. So what we did here is that we use the coordinates of the endpoints. We use the values of the endpoints, which are an x value of -1 and an x value of 7, because those are the outer limits of the domain. We basically use those to substitute into the quadratic equation in its vertex form to find the corresponding value of y. Because again, the quadratic equation in its vertex form is really y equal to that quadratic equation in vertex form. Or we could have substituted those endpoints into the original quadratic equation here, and it wouldn't have affected our answer. We would get the same answers. So we can now go ahead and proceed with the construction of the graph. There's one other minor bit of detail, minor but important bit of detail we will need to observe, but we can go ahead and plot. So going ahead to plot here, we're going to have -1 going up to 14. So I'm going to scale this at this axis right here. We're going to go up to 14 on this line. Okay, so we're going to go up to 14. I'm going to go by 2 in the interest of the space here, but it will still be fine for illustrative purposes. I'm going to go up by 2 to 4 to 6, 8, 10, 12, and finally 14. So, of course, this is the origin, which is 0. So now I'm going to plot what I have. So I'm going to plot, we have already drawn our line of symmetry, x equals 3, through the x value 3. A vertical line passing through the x value of 3 is the line of symmetry. So we've drawn that already. And we've also identified the vertex or turning point of the curve, which is hk, which is 3, -2. That's all plotted here already. So the next thing that we're going to do is that we're going to now plot the y-intercept. So the y-intercept is 0 to 7, which is going to be right here between 6 and 8. So that's the y-intercept, 0 to 7. Let's just label that 0, 7. That's the y-intercept. 0 to any value, and x value of 0 to any value will be on the y-axis. And this is where the graph is going to cut the y-axis. Also, we need to draw the endpoints of the curve. And the endpoints of the curve were found by substituting the lower and upper limit of the range that we're given, of the domain that we're given. Substituted the lower and upper limit of the domain that we're given, which is -1 and 7. We're substituting those. We substituted those into the quadratic equation in vertex form, and we got these coordinates here. -1, 14. So I'm going to plot here -1, 14. This is going to be an end point, which means that that is as far as the curve is going to go on that side. And on the other side, we have 7, 14. So I'm going to go here 7 up to 14. And there we have it. What you realize is that this mirror line that we constructed is exactly midway between this point here, this end point here, and this end point here. Alright? And so we can go right ahead now and we can connect our points. So I'm going to draw from there. I'm going to pass through the y-intercept. I'm going to go down to the turning point. And then, of course, having gone down to the turning point here, we will turn upwards and we will go up to the other end point on the other side of the symmetric parabola that we have constructed here. And this is a sketch of our graph f of x. This is how we can derive the sketch of our graph for f of x. Critically, we were asked to exhibit the minimum point, which we did here, 3, -2. We also exhibited the y-intercept, which is 0, 7, and we exhibited the axis of symmetry. We also went further and computed the coordinates of the endpoints, which are these. And this represents a sketch. That's really what it is. It's a sketch. It's not a graph that is drawn perfectly to scale by any stretch of the imagination, but that's not what was required either. We were simply asked to sketch the graph of the function. And this is a satisfactory sketch for this problem. So this is how we treat with these questions. They are fairly involved, but very common questions that are confronted with in these papers. So I hope you found this to be very instructive, and you're going to take a shot at this one. This is a practice question that I'm going to ask you to work on now. You're given the quadratic equation f of x or y equals 2x squared minus 8x plus 5. And you're asked similarly to express it in vertex form. A into x minus h. Let me insert the a here. You're asked to express it in vertex form. A into x minus h plus k. Then state the minimum value of the function and then sketch the graph of the function showing the vertex and the y-intercept. Remember that the vertex is the turning point of the graph, okay? That's what the vertex is, it's the turning point. So don't forget the a here. So it's a into x minus h all squared plus k. That is the vertex form for the quadratic function. All right, so you're going to take a shot at this to practice, so sharpen your skills and demonstrate your understanding of this lesson. And I will be doing another lesson that presents the solution to this problem. Thank you very much.